All right, so let's continue our theme of adding things across double bonds. In this case, we're going to take a look at catalytic hydrogenation. And hydrogenation basically means that we're going to add two H's across our double bond. And so we've got our generic alkene. And what we're going to do is add some H2 gas and then some sort of catalyst, usually platinum, nickel, or palladium. And so this thing can be platinum, palladium, or nickel. Either one of them, we will add two hydrogens across this double bond and reduce it down to an alkane. So again, we're going from an alkene to an alkane. And so the way this works, this is a heterogeneous catalyst. What that means is that it's a solid, right? So we have our catalyst right here. And then the first thing it does, it absorbs some H2 molecules across here and then breaks them up into basically just single hydrogens. All right, so we got an H, got an H. And then the pi bond of this alkene will be attracted to our catalyst as well. And then we're going to go ahead and add our hydrogens to the alkene to make it an alkane at the end. And similar to our boration, we have syn addition of these hydrogens. So for example, if we have this cyclic alkene, we add some H2 with a palladium catalyst. We'll add them syn, right? So both of these methyl and ethyl groups will either point up or they'll point down, right? You'll end up with this pair of enantiomers. Be careful with alkenes that are symmetric. Here, when we add some hydrogen and some palladium, we only end up with one product. And the reason we only end up with one product is because this compound is meso. And so it does not really have an enantiomer, right? It has a mirror image, but the mirror image is itself. And so again, you can use different catalysts here. Sometimes you'll see like palladium on carbon as a common one, but again, you can use platinum, palladium, or nickel. And these are all heterogeneous catalysts, right? So they're solids and our substrates are in solution, right? Not necessarily aqueous because it's not water, but in solution. We can also use a homogeneous catalyst. And that's this ruthenium complex. It has one chlorine and three triphenylphosphines, right? So the P is a phosphorus and the pH is a phenyl or an aromatic or a benzene group, right? But it still undergoes syn addition. And this is known as Wilkinson's catalyst. So if you see hydrogen or H2 and Wilkinson's catalyst, it's just a hydrogenation. If this word hydrogenation seems familiar to you, it's used in industry and kind of fast food, and not just fast food, but other things as well. This right here would be what's known as a fatty acid, right? So it's a carboxylic acid and then a alkyl chain. And so in this case, we have this alkene, this double bond, and so we call this an unsaturated fat. And so it's not saturated with hydrogens, right? There's places where these carbons could add more hydrogens to them. These compounds are liquid at room temperature, right? And the reason is these intermolecular forces, they can't pack as well. due to the rigidity of the double bonds. And so in industry and in kind of fast food, what they do is they hydrogenate these fats, right? So we go from an unsaturated fat with alkenes to a saturated fat, right? So it's saturated with hydrogens, and these things are solid at room temperature and also maybe inside of your arteries, right? The reason they do this is because these solids have longer shelf lives. So it's kind of, reduced cost type of thing. And so that's kind of, one negative of these hydrogenation. You go from these unsaturated fats to these saturated fat. And then these things also have a tendency to saturate cis alkenes over trans alkenes. And so if you just partially hydrogenate them, what you're left with is a lot of trans alkenes, and that, in relation is then trans fats, which are, quote unquote, bad for you health-wise. So just kind of, a good connection between what we're learning about here and real life application.